You are listening to Beyond the Build, mastering CI/CD for faster, safer software delivery. Subscribe to keep up to date on our latest audiobooks. Beyond the Build, mastering CI/CD for faster, safer software delivery. Chapter 1, Welcome to the Flow, Why CI/CD Matters More Than Ever. 1.1, The Software Delivery Challenge. A call for change. In the world of software, speed often feels like the ultimate currency. Businesses constantly strive to bring innovations to market faster, respond to customer needs more swiftly, and adapt to changing conditions with agile precision. Yet, for many years, the process of turning an idea into working software that customers could actually use was fraught with hurdles. 1.1.1 The Old Way. Manual, monolithic, and painful releases. Imagine a scenario. A software development team works diligently for months to build a new feature or an entire application. Developers toil on their individual pieces of the puzzle, often in isolation. Once their work is done, the grand merging begins. This is where the term integration hell often surfaced. Tens or even hundreds of disparate code changes, each made by a different developer, would be brought together for the first time. The results were predictable: conflicting code, broken features, and a cascade of unforeseen errors. This painful, drawn-out process could take days, sometimes weeks, to resolve. Debugging became a frantic race against the clock, as various teams pointed fingers, seeking the elusive bug. Once the code was finally integrated, a separate team, often operations specialists, would then manually transfer the software to various test environments. This involved carefully following step-by-step checklists, meticulously copying files, and configuring servers. Each environment had its own subtle differences, leading to the infamous "it works on my machine" problem, where code that ran perfectly on a developer's computer crashed spectacularly in a test environment. The culmination of this long, arduous journey was the release day. This wasn't merely a day, it was often a weekend or an entire week of high-stakes, all-hands-on-deck effort. Teams would be on standby, fueled by caffeine and anxiety, ready to troubleshoot any issue that arose from the manual deployment. Downtime was expected, stress levels were high, and the threat of a major outage loomed large. If a critical bug slipped through, fixing it meant another agonizing journey through the entire process. This traditional approach was slow, expensive, risky, and a continuous source of frustration for everyone involved. It drained innovation and stifled the ability to respond to market demands. 1.1.2 The Modern Imperative. Speed, quality, and adaptability. The world, however, did not stand still. The internet era brought unprecedented interconnectedness and consumer expectations. Users now expect seamless experiences, constant updates, and instant gratification. Companies like Amazon, Google, and Netflix showcase the power of rapid iteration, deploying new features and bug fixes multiple times a day, without interruption. This set a new benchmark for software delivery. For any business to thrive in this environment, it became clear that the old ways were no longer sustainable. There was a critical need for software teams to deliver value faster than ever, without compromising on quality or stability. They needed to move from infrequent, risky, big bang releases to a model of continuous, reliable delivery. This imperative gave rise to continuous integration and continuous delivery practices that have reshaped the landscape of software development. 1.2 Introducing CI/CD. The pillars of modern software delivery. Continuous integration and continuous delivery, often referred to collectively as CI/CD, represent a fundamental shift in how software is built, tested, and deployed. They are not merely tools or technologies, but rather a set of principles and practices that form a powerful pipeline, transforming the painful old way into a smooth, automated flow. 1.2.1 What is continuous integration, CI? At its core, continuous integration, CI, is the practice of merging all developers' working copies of code to a shared main branch, often called the main or trunk, often, ideally, multiple times a day. Instead of letting developers work in isolation for weeks, CI encourages them to integrate their small, incremental changes frequently. The moment a developer commits their code change to the central repository, an automated process springs into action. This process, typically orchestrated by a CI server, automatically performs a build. Building software involves compiling code, packaging it, and running a suite of automated tests. If the build or any of the tests fail, the team is immediately alerted, and developers are expected to fix the issue as quickly as possible. The core idea behind CI is simple yet profound. Integrate early, integrate often. By detecting integration issues within minutes or hours of their introduction, rather than weeks or months, teams can resolve them quickly before they escalate into major problems. This drastically reduces the risk of integration hell and ensures that the codebase is always in a healthy, working state. The benefits are clear: early bug detection, fewer merge conflicts, a more stable codebase, and peace of mind for developers. 1.2.2 What is continuous delivery, CD? Continuous delivery, CD, extends the principles of CI. While CI ensures that your code is always integrated and tested, CD takes it a step further. It ensures that your software is always in a deployable state. This means that at any given moment, the software sitting in your repository, having passed all automated tests, is ready to be released to a production environment or any other environment, like staging or testing. The philosophy of CD is to make releases boringly routine. Instead of a high-stress event, a release becomes a simple, automated action that can be performed at the push of a button or even automatically. This requires comprehensive test automation that covers not just functionality, but also performance and security. It also demands automated deployment mechanisms that can reliably and consistently push the software to various environments. The main benefits of CD are faster time to market, since releasing new features becomes trivial, and significantly lower deployment risk. Because each release involves only small, incremental changes that have been thoroughly tested in an environment mirroring production. It effectively means you can deploy a specific version of your software whenever you choose, with high confidence in its stability. It's important to note a subtle but significant distinction here. Continuous delivery means the software is always capable of being deployed. Continuous deployment takes it one step further by automatically deploying every change that passes all automated tests all the way to production, without human intervention. Continuous delivery gives you the option to release at will, while continuous deployment means every verified change goes live automatically. We'll delve deeper into this distinction in a later chapter. 1.2.3 Why continuous? The power of iteration and feedback. The word continuous in both CI and CD is key. It signifies a move away from large, infrequent batch processes to a steady, iterative flow. Instead of developing features in isolation for months and then performing a massive, risky release, CI/CD advocates for continuous iteration. Small changes, frequent integration, rapid testing, and the ability to deploy at any moment. This continuous flow is powered by incredibly fast feedback loops. If something goes wrong, a test fails, a bug is introduced, performance degrades, the team knows about it almost instantly. This immediate feedback allows for quick correction, preventing small issues from escalating into major problems. It's like gently steering a ship with tiny rudder adjustments, rather than waiting until you're veering wildly off course to make a sudden, drastic correction. This iterative approach fosters a culture of continuous learning and improvement, making the entire software delivery process more predictable and less stressful. 1.3 The transformative power. Benefits of adopting CI/CD. The adoption of CI/CD is more than just a technical upgrade. It's a strategic advantage that can fundamentally transform how an organization delivers software and, by extension, innovates. 1.3.1 Speed. Accelerating time to market. Perhaps the most immediately tangible benefit of CI/CD is the dramatic acceleration of software delivery. By automating builds, tests, and deployments, the bottlenecks that traditionally plagued software development are removed. New features can be developed, integrated, tested, and released to users in hours or days, not weeks or months. This rapid iteration allows companies to respond to market changes, competitor actions, and customer feedback with unprecedented agility, gaining a significant competitive edge. Imagine being able to roll out a new product enhancement within days of conceiving it, rather than waiting an entire quarter. 1.3.2 Quality, enhancing software reliability. CI/CD inherently drives higher software quality. The emphasis on automated testing at every stage, from unit tests in CI to comprehensive system tests in CD, means that defects are caught early and often. Developers receive immediate feedback if their changes introduce regressions or new bugs. This shift-left approach to quality, where testing happens earlier in the development lifecycle, drastically reduces the number of defects that reach production environments. The result is more reliable, robust software that performs consistently for users. 1.3.3 Risk reduction, making deployments boringly routine. One of the greatest fears for any software team is a bad deployment that impacts users or critical business operations. CI/CD transforms this fear into confidence. By making small, incremental changes and deploying them frequently, the risk associated with each individual deployment is significantly reduced. If a problem does arise, it's easier to pinpoint the cause, because the change set is small, and to quickly roll back to a known good version. Deployments cease to be high-stakes, all-night events and become predictable, automated procedures that can be conducted during normal business hours without drama. 1.3.4 Collaboration and team morale, building a harmonious environment. Beyond the technical benefits, CI/CD fosters a healthier and more collaborative work environment. When integration issues are caught automatically and quickly, developers spend less time debugging legacy problems and more time building new features. The shared responsibility for the health of the build empowers the team, leading to a sense of collective ownership. Reduced stress from release day and an increase in successful deployments boost morale and foster a more positive, innovative team culture. Developers gain confidence in their work, knowing that their changes are validated immediately. 1.4 Beyond the buzzwords, CI/CD as a culture and mindset. It's tempting to view CI/CD as simply a collection of tools and technologies. While tools are undoubtedly important enablers, the true power of CI/CD lies in the philosophical and cultural shift it represents. 1.4.1 Not just tools. Principles over products. You could have the latest and greatest CI/CD tools, but without embracing the underlying principles of frequent integration, comprehensive automation, fast feedback, and continuous improvement, you won't reap the full benefits. CI/CD is about discipline, collaboration, and a commitment to quality throughout the entire development lifecycle. It's about building a robust pipeline that not only automates tasks, but also enforces crucial development practices. This shift in mindset from manual, isolated work to automated, collaborative flow is paramount. 1.4.2 The DevOps connection. CI/CD as a cornerstone. CI/CD is often discussed in the context of DevOps. DevOps is a set of practices that combines software development, dev, and IT operations, ops, to shorten the system's development lifecycle and provide continuous delivery with high software quality. CI/CD is a cornerstone, perhaps the cornerstone, of DevOps. It provides the technical mechanism through which the collaboration and automation principles of DevOps are implemented. Without effective CI/CD, achieving true DevOps maturity is extremely challenging. By embracing CI/CD, organizations are effectively adopting core tenets of modern DevOps culture. 1.5 What this book will teach you. This book is your guide to understanding, implementing, and optimizing continuous integration and continuous delivery. We will demystify the concepts, explore the different components of a CI/CD pipeline, and outline the best practices that lead to successful adoption. You will learn the fundamental principles that underpin CI/CD, how different tools fit into the CI/CD ecosystem without getting lost in tool-specific instructions, strategies for building robust and reliable automated tests, approaches for deploying software with confidence and minimal risk, how to integrate security and monitoring throughout your pipeline. Crucially, you'll understand why CI/CD is not just about technology, but also about people, processes, and a culture of continuous improvement. Our goal is to provide you with the conceptual framework and practical knowledge needed to embark on your own CI/CD journey or to enhance your existing practices. We'll focus on the why and the what, providing you with the enduring understanding you need, rather than tool-specific how-to guides that quickly become outdated. By the end of this book, you will have a comprehensive understanding of how CI/CD empowers teams to deliver faster, safer, and higher quality software, enabling your organization to thrive in the fast-paced world of technology. Let's begin the journey. Chapter 2, The Heartbeat of Development, Understanding Continuous Integration, CI. In our journey to understand continuous delivery, we must begin with its foundational pillar, continuous integration. CI is more than just a software practice. It's a commitment to a specific way of working that dramatically improves the health and stability of your codebase. 2.1 The problem CI solves. Integration hell. To truly appreciate continuous integration, let's revisit the problem it was designed to fix. Before CI became a widespread practice, software development often resembled a relay race with too many runners and not enough handoffs. 2.1.1 The days of batch integration. Long cycles, big bang merges. Imagine a team of developers, each working on their own isolated piece of a software puzzle. Developer A builds a new user interface, Developer B crafts a complex algorithm, and Developer C connects to a new database. Each works in their own virtual sandbox, making changes to the code without immediate concern for what others are doing. This might go on for days, weeks, or even months. Then comes the dreaded integration phase. This is the moment when all those isolated changes are finally brought together and attempted to be merged into a single, cohesive application. This process often led to what developers grimly referred to as integration hell. Code conflicts would abound, where changes made by one developer inadvertently broke functionality built by another. It was like trying to assemble a complex machine where each part was manufactured by a different person without seeing anyone else's blueprints. This approach was not only inefficient, but also highly stressful. Discovering a conflict late in the cycle meant expensive debugging and rework. The longer the time between integrations, the more extensive the changes, and the harder it became to identify and fix the source of problems. The collective codebase often remained in an unstable, non-functional state for extended periods, making it impossible to confidently test the complete system. 2.1.2 Consequences. Broken builds, delayed releases, costly debugging. The fallout from integration hell was severe. Broken builds, the combined codebase simply wouldn't compile or run, halting all further progress. Delayed releases. Weeks of effort could be lost trying to untangle hidden dependencies and resolve unexpected behavioral changes. Costly debugging. Pinpointing the exact change that introduced a bug among thousands of lines of new code committed by multiple developers was like finding a needle in a haystack, an extremely expensive haystack. It works on my machine? The frustrating reality that code working perfectly on a developer's local computer would break when combined with others' work, or when moved to a shared environment. This dysfunctional cycle created an environment of fear and unpredictability, dampening innovation and making software delivery a gamble rather than a reliable process. 2.2 Defining continuous integration. Principles and practices. Continuous integration emerged as a direct solution to integration hell. Its core philosophy is elegantly simple. If integration is painful, then do it more often. 2.2.1 The core idea. Integrate early, integrate oft. At its heart, continuous integration is the practice of frequently merging all developers' code, changes into a single, shared main branch of a version control system, VCS. This isn't just a suggestion, it's a discipline. Developers are encouraged to commit small, incremental code changes several times a day, thereby avoiding the accumulation of large, conflicting code masses. Every time code is committed, an automated process immediately kicks off. This process typically involves compiling the code, running automated tests, and providing instant feedback on the health of the entire application. If any part of this automated check fails, be it a compilation error or a broken test, the entire team is notified immediately. The golden rule of CI is to fix broken builds immediately. Do not add new code on top of a broken system. Instead, stop, resolve the issue, and ensure the main branch is in a working state before proceeding. This constant vigilance provides incredibly fast feedback. Instead of finding out about a critical integration issue weeks later, it's discovered within minutes. This allows developers to tackle problems when they are small and easy to resolve, directly impacting the code they just wrote. 2.2.2 Jez Humble and David Farley's Principles of CI. While the concept of CI has evolved, its foundational principles were clearly articulated by thought leaders like Jez Humble and David Farley. They proposed a set of practices that, when consistently applied, underpin a robust CI system, maintain a single source repository. All code lives in one central, accessible location. Automate the build. The process of compiling code and turning it into a usable artifact should be fully automated. Make the build self-testing. This is crucial. Every build must automatically trigger a suite of tests to verify functionality. Everyone commits to the mainline every day. Small, frequent integrations are key to avoiding merge conflicts and detecting issues early. Every commit should build the mainline on an integration machine. A dedicated, clean environment ensures consistency. Fix broken builds immediately. Prioritize resolving issues found by the CI system above all else. A broken build means no one can integrate their changes, effectively halting progress. Keep the build fast. If builds take too long, developers will be discouraged from committing frequently. Test in a clone of the production environment. The environment used for integration testing should closely resemble the final production environment to catch discrepancies early. Make it easy for everyone to get the latest executable. Developers should be able to quickly retrieve the most up-to-date, tested version of the software. See what's happening. Make the results of the CI process transparent and visible to the entire team. Adhering to these principles transforms the chaotic integration phase into a streamlined, nearly invisible process that runs constantly in the background, serving as the steady heartbeat of your development efforts. 2.3 Key components of a CI system. A successful CI system isn't a single piece of software. It's an ecosystem of interconnected tools and practices that work in harmony. 2.3.1 Version Control System, VCS, the foundation of collaboration. At the bedrock of any CI system is a robust version control system, VCS. Tools like Git, the most widely used, Subversion, or Mercurial serve as the single source of truth for your codebase. They allow multiple developers to work on the same project simultaneously, track every change, and manage different versions of the code. For effective CI, the VCS makes frequent integration possible. Developers commit their changes, essentially saving a snapshot of their work, and then push these changes to the central repository. The VCS also provides mechanisms for merging changes from different developers, though CI aims to make these merges small and manageable. A common strategy for CI is trunk-based development, where all developers commit directly to the main development branch, the trunk, or main, multiple times a day, keeping divergence to a minimum. 2.3.2 Build automation, turning code into deliverables. Once code is committed to the VCS, the next crucial step is build automation. This is the process of automatically transforming your human-readable source code into a usable software artifact, whether it's an executable program, a library, a web application, or a Docker image. Build automation tools and scripting frameworks like Maven and Gradle for Java, NPM for JavaScript, or simpler shell scripts handle tasks such as compilation, converting source code into machine-readable instructions, dependency management, ensuring all external libraries and frameworks needed by the code are present, packaging, bundling the compiled code and resources into a deployable format, static analysis, checking code for common errors, style violations, and potential security vulnerabilities without actually running it. The goal is a reproducible build. Anyone, anywhere, should be able to trigger the build process and get the exact same output every time, ensuring consistency and reliability. 2.3.3 Automated testing, the first line of defense. Automated tests are the backbone of CI. Without them, a successful build merely means the code compiles. It doesn't guarantee it actually works as intended. These tests run automatically as part of the CI pipeline, providing rapid feedback on the correctness and stability of the system. The most common types of automated tests in a CI context include unit tests. These are small, fast tests that verify individual components or functions of the code in isolation. They check if the smallest building blocks of your software work correctly. Integration tests. These tests verify that different components or modules of the application work correctly together. For example, testing if the application can successfully interact with a database or an external service. The speed of these tests is paramount. Fast tests allow for frequent execution, providing immediate feedback and ensuring that any introduced bugs are caught almost as soon as they appear. The concept of a test pyramid often applies here. A large base of fast unit tests, a smaller number of slightly slower integration tests, and even fewer, comprehensive end-to-end tests. 2.3.4 CI Server Orchestrator, the conductor of the symphony. The CI server, sometimes called a CI orchestrator or pipeline engine, is the central hub that coordinates all the CI activities. It continuously monitors the version control system for new code commits. When a new commit is detected, the CI server automatically triggers the build process. Its responsibilities include fetching the latest code from the VCS, executing the automated build scripts, running the suite of automated tests, collecting results and generating reports, notifying developers and teams about build statuses, success, or failure, storing successful build artifacts for later use. Popular CI servers include Jenkins, a highly flexible open-source option, GitLab CI/CD, integrated into GitLab, GitHub Actions, integrated into GitHub, Circle CI, and Travis CI. While each has its unique features, their core function remains the same: to automate and oversee the CI workflow. 2.3.5 Artifact Management. Storing the outputs. A successful CI run produces an artifact, the packaged, tested output of your build process. This might be a deployable application package, a library, a Docker image, or a compiled binary. Artifact management involves securely storing these artifacts in a dedicated repository. Why is this important? Reproducibility. You can always retrieve a specific version of your software that corresponds to a successful build. Traceability. You know exactly which code version, tests, and build process created a particular artifact. Efficiency. Artifacts from earlier stages, e.g., CI, can be directly used by later stages, e.g., continuous delivery, without needing to rebuild. Tools like Nexus or Artifactory are examples of artifact repositories that handle this organized storage and retrieval, ensuring that every tested build is ready for the next stage of the delivery pipeline. 2.4 The CI process in action, a walkthrough. Let's illustrate the continuous integration process with a simple step-by-step flow. Developer commits code. A developer finishes a small piece of work, writes an accompanying unit test, and commits these changes to the team's shared version control system, e.g. Git. CI server detects change. The CI server, which constantly monitors the VCS, detects this new commit. Build triggered. The CI server automatically pulls the latest code, including the new changes, onto a dedicated build machine. Code building. The build automation tools compile the code, resolve dependencies, and perform any static analysis checks. Automated testing. Immediately after a successful compilation, the CI server executes the comprehensive suite of automated tests, unit tests, integration tests, results and notifications. If the build or any tests fail, the CI server instantly notifies the relevant team, e.g., via chat, email, or a dashboard. The team immediately stops what they're doing to fix the issue. A common practice is to fix the build within minutes, not hours, as a broken build impacts everyone. If the build and all tests pass, the CI server marks the build as successful. The newly created software artifact is stored in the artifact repository, making it available for future use. The team has confidence that the main codebase is stable and healthy. This cycle repeats constantly throughout the day, providing an uninterrupted stream of feedback on the quality and stability of the software. 2.5 Benefits of a robust CI implementation. The consistent application of continuous integration yields a multitude of advantages. Early detection of defects. Bugs and integration issues are caught within minutes or hours rather than days or weeks, significantly reducing the cost and effort required to fix them. Improved code quality. The constant feedback loop incentivizes developers to write cleaner, more testable code. Static analysis tools also help identify bad practices early. Reduced technical debt. By keeping the code base stable and well-tested, CI prevents the accumulation of technical debt that often arises from rushed, unintegrated changes. Increased confidence in the codebase. Developers and stakeholders gain high confidence that the main branch is always in a working, deployable state. This eliminates the fear of merging. Supports faster development paces. With reliable integration and immediate feedback, developers can work faster and more confidently, knowing their changes are being validated continuously. Enhanced team collaboration. CI fosters a culture of shared responsibility for the health of the build, promoting better communication and collective problem-solving. 2.6 Common pitfalls and how to avoid them. While the benefits of CI are compelling, there are common missteps that can hinder its effectiveness. Broken builds are ignored. The most critical principle of CI is to fix broken builds immediately. If a broken build lingers, the system loses its value and developers revert to working in isolation. Establish clear team agreements on who is responsible for fixing broken builds and how quickly. Long-running builds. If the entire CI process, fetch, build, test, takes too long, e.g., more than 10 to 15 minutes, developers will be reluctant to commit frequently. Optimize build scripts, run tests in parallel, and invest in faster build infrastructure. Insufficient test coverage. A build that passes but doesn't run enough meaningful tests provides a false sense of security. Invest time in writing comprehensive, automated unit and integration tests. Too many manual steps. Any manual steps in the build or preliminary testing process add friction, introduce human error, and negate the benefits of automation. Automate everything that can be automated. Ignoring feedback. The CI server yells for a reason. If team members are not paying attention to notifications or build statuses, critical issues will slip through. Ensure build status is highly visible, e.g., on dashboards in team chat. By understanding these principles, components, and potential pitfalls, you can lay a strong foundation for continuous integration, ensuring that your development efforts maintain a healthy and consistent heartbeat, always ready for the next stage of the delivery pipeline. Chapter 3, Delivering Value Continuously. Understanding Continuous Delivery, CD. We've seen how continuous integration, CI, provides the essential foundation, a code base that is always integrated, always tested, and always in a known good state. But having a continuously integrated and tested artifact is only half the battle. The true value of software is only realized when it's in the hands of the users. This is where continuous delivery, CD, steps in. 3.1 Beyond integration. The need for automated deployment. Think back to the integration hell we discussed in the last chapter. Even if you've mastered CI and your codebase is constantly healthy, getting that working software out to users can still be a nerve-wracking, error-prone ordeal. 3.1.1 The release problem. Manual, error-prone, and stressful. Many organizations, even those practicing some form of CI, still face a significant bottleneck at the deployment stage. This often involves a long, detailed checklist of manual steps. Logging into various servers, copying files, updating configuration settings, running database scripts, restarting services, and then painstakingly verifying each step. This process is frequently executed by a small group of operations specialists, often outside of normal working hours, to minimize disruption. Consider the consequences. Release fear. Because each deployment is a manual, high-stakes affair, teams become risk-averse. They try to cram as many features and bug fixes as possible into a single, massive release to avoid frequent deployments. Inconsistent environments. Manual processes are prone to human error. A typo in a configuration file, a skipped step in a checklist, or a difference in server setup between testing and production environments can lead to unexpected failures. The classic "it works in staging but not in production" problem. Human error. No matter how careful, humans make mistakes, especially under pressure. These mistakes can lead to downtime, data corruption, or security vulnerabilities. Costly delays. If a problem occurs during a manual deployment, finding and fixing it can take hours or even days, delaying the release and negatively impacting users and business. This release process, rather than being a celebration of new features, often becomes a dreaded, stress-filled experience. It is the final barrier blocking the fast delivery of value that CI promises. 3.1.2 The vision. Always ready for release. Continuous delivery tackles this final mile. Its vision is simple yet transformative: to ensure that your software is always in a state where it can be confidently and reliably released to production or any other environment at any time with minimal effort and maximum automation. This means moving from "we hope it works when we deploy" to "we know it works, and we can deploy it right now if we choose." 3.2 Defining continuous delivery. Principles and goals. Continuous delivery takes the fully integrated and tested artifact produced by CI and shepherds it through a series of automated gates, ending with it being ready for release. 3.2.1 The core idea. Deployable at will. The central tenet of continuous delivery is that every change, no matter how small, that passes through your CI pipeline is a potential release candidate. This means the software is always stable, always tested, and always ready to be pushed to end users. The act of deployment itself becomes automated, repeatable, and reliable. You can make the strategic business decision to release, and the technical mechanisms are already in place to execute it swiftly and safely. 3.2.2 Key principles. Several guiding principles define continuous delivery. Every change goes through the pipeline. Even minor code tweaks or configuration changes must pass through the full automated pipeline to ensure quality and consistency. Automate everything that can be automated. From building and testing to deployment and environment provisioning, manual steps are bottlenecks and sources of error. Build once, deploy many times. The exact same software artifact built by CI should flow through all environments: development, testing, staging, and finally production, without modification. This prevents "works on my machine" and "works in staging" issues. Fast, reliable, and frequent releases. The goal is to make releasing new versions so easy and low risk that it can be done frequently, even many times a day if desired. Comprehensive monitoring and feedback. Once deployed, the application must be monitored proactively to detect issues immediately, and this feedback must continuously inform future development. 3.3 Continuous delivery versus continuous deployment. A key distinction. While often used interchangeably or conflated, it's crucial to understand the difference between continuous delivery and continuous deployment. The distinction lies in the final step to production. 3.3.1 Continuous delivery. Human decision for production release. With continuous delivery, your pipeline ensures that the software is always in a release-ready state. It has passed all automated tests, been deployed to various non-production environments, like staging, and is deemed stable. However, the decision to actually push that version to the live production environment is still a manual one. There's a human or business process approval gate before the final deploy button is pressed. This model is ideal for many organizations, especially those with strict regulatory requirements, extensive compliance checks, or a need for a dedicated marketing push around new features. For example, a bank might use continuous delivery to ensure their internal systems are always ready for deployment, but only push updates to production after a senior compliance officer's sign-off. 3.3.2 Continuous deployment. Automated production release. Continuous deployment takes continuous delivery to its ultimate conclusion. Every change that successfully passes through the automated CI/CD pipeline is automatically deployed to production without human intervention. If a change passes all tests and meets all criteria, it goes live. This requires an extremely high level of confidence in your automated testing suite, your monitoring capabilities, and your ability to quickly roll back any issues that might arise. Companies like Netflix, Amazon, and Google are famous proponents of continuous deployment, releasing new code to production countless times a day. For example, a minor bug fix in an internal tool might go straight to production within minutes of being committed, if all automated checks pass. 3.3.3 Making the choice. Factors to consider. The choice between continuous delivery and continuous deployment depends on several factors. Risk tolerance. Continuous deployment carries higher risk if your automated tests aren't robust or your monitoring isn't sufficient. Regulatory requirements. Certain industries, healthcare, finance, may have regulations that mandate human review or specific release windows. Business model. For a purely digital product with frequent iterative updates, continuous deployment might be ideal. For a product tied to physical goods or requiring extensive customer training, continuous delivery might be more appropriate. Team maturity. Moving to continuous deployment requires a deeply ingrained culture of quality, automation, and immediate response to issues. Most organizations start with continuous delivery, mastering it before considering the leap to full continuous deployment. The benefits we discuss for CD apply equally to both, as continuous deployment is simply a further automation of continuous delivery. 3.4 Key components of a CD system. Building upon the foundation of CI, a robust CD system introduces several new layers of automation and orchestration. 3.4.1 Deployment automation, the hands-free release. This is the core of continuous delivery. It involves automating the actual process of moving the validated software artifact from your artifact repository, where it landed after CI, to various environments. This includes provisioning infrastructure, setting up or configuring servers, virtual machines, or cloud resources. This often involves infrastructure as code, ISC tools. ISC treats your infrastructure configuration like regular code. It's version-controlled, testable, and automated. Tools like Terraform, Ansible, or Puppet allow you to define your infrastructure programmatically, ensuring consistency across environments. Application deployment, copying application files, updating databases, configuring web servers, and starting services. These are typically managed by deployment scripts or specialized deployment tools. Rollback procedures. Critically, an automated deployment system must also have an automated rollback mechanism to quickly revert to a previous stable state if a problem is detected. The goal is to ensure that a push-to-deploy button or an automated trigger reliably executes all necessary steps every single time without human intervention. 3.4.2 Environment management. Consistent stages for progress. For software to reliably move from development to production, the environments it runs in must be as consistent as possible. Continuous delivery emphasizes creating highly similar environments for development, testing, staging, pre-production, and production. Environment mirroring. The closer your non-production environments resemble production in terms of hardware, software, network configuration, and data, the fewer surprises you'll encounter during deployment. Containerization. Technologies like Docker allow you to package your application and all its dependencies, libraries, configuration, etc., into a portable, standardized container. This container can then run consistently in any environment, significantly reducing works on my machine issues. Orchestration. For managing and scaling containers across multiple servers, tools like Kubernetes, a container orchestrator, automate deployment, scaling, and operational tasks, making environment management highly programmable. Leveraging these technologies makes environments disposable, easily rebuildable, and consistent, further reducing risk during deployment. 3.4.3 Release orchestration. Managing the flow. While CI focuses on what happens around each code commit, release orchestration manages the entire journey of a release candidate through the pipeline. This includes defining the sequence of stages, e.g., build, test, deploy to dev, deploy to staging, deploy to production, and the gates between them. The CI/CD server introduced in Chapter 2, along with specialized release orchestration tools, allows you to define approval steps for moving between stages, Track the status of releases. Promote specific versions of your software through different environments. Integrate with other systems, e.g., ticketing systems, notification services. The pipeline becomes a clear visual representation of your software's journey to production, providing transparency and control. 3.4.4 Monitoring and Alerts. Observing the health of deployments. Once software is deployed, especially to production, the job isn't done. Continuous delivery relies heavily on robust monitoring and alerting systems to confirm that the deployment was successful and that the application is performing as expected. Application Performance Monitoring, APM, tools that track metrics like response times, error rates, CPU usage, memory consumption, and network traffic. Log Management, centralized systems for collecting, storing, and analyzing application logs to identify issues. Business Metrics, tracking key performance indicators, KPIs relevant to the business, such as user conversions, sales, or signups, to ensure the new release is positively impacting business goals. If any anomalies are detected, automated alerts notify the team immediately, allowing for rapid response and, if necessary, an automated rollback. 3.4.5 Feedback Loops. Learning and improving. The final, crucial component of continuous delivery is the feedback loop. Data from monitoring, user feedback, and post-incident reviews are fed back into the development process. This allows teams to continuously identify areas for improvement in the software itself, the development process, and the CI/CD pipeline. This iterative learning is what truly makes the delivery continuous. 3.5 The CD process in action. A walkthrough. Let's trace the journey of a single change through a continuous delivery pipeline. CI success. A developer commits code. The continuous integration process, as described in Chapter 2, automatically builds the software, runs all unit and integration tests, and confirms the main branch is stable. A deployable artifact is created and stored in the artifact repository. Automated deployment to development test. The CI/CD pipeline automatically deploys this newly built artifact to a dedicated development or test environment. Automated testing in test environment. A more extensive suite of automated tests runs here, including system tests, regression tests, and potentially some performance or security scans. These tests ensure the application functions correctly in an environment closer to real-world usage. Deployment to staging pre-production. If the tests in the test environment pass, the exact same artifact is then automatically deployed to a staging or pre-production environment. This environment should be as close a replica of the production environment as possible. Further testing in staging. In staging, more elaborate tests might occur, potentially including user acceptance testing, UAT by business stakeholders, extensive performance testing, and final security audits. Human approval for continuous delivery. At this point, the pipeline pauses. A human decision maker, e.g., a product manager, release manager, or even the development team lead, reviews the results of all tests and confirms that the software is ready for production. This is the manual gate that defines continuous delivery. Automated production deployment. Once approved, the pipeline automatically deploys the software to the production environment. This is often done using strategies like blue-green deployments or canary releases to minimize risk and downtime. We'll explore these strategies later. Monitoring in production. After deployment, the monitoring systems are actively observing the application's performance and behavior in the live environment. Feedback loop initiates. Any issues detected in production or insights gained from user behavior are immediately fed back into the development process, sparking a new cycle of iteration and improvement. This systematic, automated progression ensures that only high-quality, thoroughly tested software makes it to live users. 3.6 Benefits of a robust CD implementation. The advantages of implementing continuous delivery are profound and far-reaching. Faster time to market. New features and bug fixes can be delivered to users in a matter of hours or days, not weeks or months, allowing businesses to respond rapidly to market demands. Reduced deployment risk and stress. Deployments become routine, automated, and less prone to human error, dramatically reducing anxiety and the likelihood of outages. Consistent and repeatable deployments. Automation ensures that every deployment follows the same steps, eliminating inconsistencies between environments and manual missteps. Empowered teams, rapid experimentation. Developers can push changes with confidence, knowing they will be validated quickly. This fosters a culture of experimentation and innovation. Improved business outcomes. Faster feedback cycles from real users allow businesses to validate ideas more quickly, pivot when necessary, and ultimately deliver more valuable products and services. Higher customer satisfaction. Users benefit from continuous improvements, faster bug fixes, and a more stable, reliable product. 3.7 Common pitfalls and how to overcome them. Despite its clear benefits, implementing CD isn't without its challenges. Inconsistent environments. Failing to maintain parity between development, test, staging, and production environments is a common pitfall. Invest in infrastructure as code and containerization technologies to ensure environments are identical and reproducible. Lack of monitoring. Deploying frequently without robust monitoring is like driving blind. Implement comprehensive APM, logging, and business metrics to quickly detect and diagnose issues in production. Ignoring security in the pipeline. Security often remains an afterthought. Integrate automated security scanning, vulnerability checks, and compliance policies directly into your CD pipeline, DevSecOps, which we'll cover later. Cultural resistance to automation. People are often comfortable with existing manual processes, especially if those are their job. Emphasize the benefits of automation while investing in training and support to help teams adapt to new ways of working. Insufficient test automation. While automated deployment is great, if the underlying test suite is weak, you're merely automating the delivery of potentially broken software. Continuously invest in improving test coverage and quality. Continuous delivery transforms your software delivery from a burdensome chore into a smooth, efficient, and reliable process. By automating the journey from committed code to deployable artifact, it ensures that true value reaches your users continuously. Chapter 4, Assembling the Pipeline, Anatomy of a CI/CD Workflow. In the previous chapters, we dissected continuous integration, CI, and continuous delivery, CD, into their core principles and benefits. Now, it's time to put the pieces together and understand how these concepts coalesce into a unified, automated system, the CI/CD pipeline. Think of the pipeline as an automated factory assembly line for your software, moving it from raw code to a deployed product with minimal human intervention. 4.1 What is a CI/CD pipeline? At its simplest, a CI/CD pipeline is an automated workflow that guides your software development process from the moment a developer commits code to the point it's deployed to production. It's a series of automated steps designed to ensure that software changes are built, tested, and deployed reliably and efficiently. The concept of a pipeline is quite literal. Much like a physical pipeline carries liquid from one point to another, a CI/CD pipeline carries your software code through various stages, transforming it and adding value at each step. If any stage in the pipeline fails, the entire process stops, signaling an issue that needs immediate attention. This ensures that only high-quality, tested code progresses through the system. The primary goals of a well-designed CI/CD pipeline are automation, reduce manual effort and human error. Consistency, ensure the same steps and checks are applied every time. Speed, accelerate the delivery of software. Quality, enforce quality gates at every stage. Visibility, make the status of software delivery clear to the entire team. 4.2 The stages of a typical CI/CD pipeline. While exact stages can vary based on project complexity and organizational needs, most CI/CD pipelines follow a common logical progression. We can break down the typical pipeline into at least 5 distinct stages: source, build, test, deploy, and monitor. 4.2.1 Stage 1. Source, the beginning of the journey. This is the trigger point, the very start of the pipeline. Trigger, the pipeline typically begins when a developer commits code changes to the version control system, VCS, like Git. This could be a new feature, a bug fix, or a configuration update. The CI/CD server is constantly monitoring the VCS for these changes. Action. When a change is detected, the CI/CD server pulls the latest version of the code. This ensures that the pipeline always operates on the most up-to-date codebase. Key components: version control system, VCS, Git, GitHub, GitLab, Bitbucket, Azure repos, etc., is almost universally used. Hooks triggers, mechanisms within the VCS or CI/CD server that initiate the pipeline upon a code commit. 4.2.2 Stage 2. Build, crafting the deliverable. Once the code is pulled, the next stage focuses on transforming the raw source code into a runnable artifact. Purpose: to compile the code, manage dependencies, and package everything into a deployable unit. This is where your code becomes a tangible product. Actions: compilation, converting human-readable code into executable binaries or interpreted scripts. Dependency resolution, downloading and linking necessary libraries or frameworks used by the application. Static code analysis, running tools that inspect the code for potential bugs, style violations, security vulnerabilities, or maintainability issues without executing it. Examples might be linting tools or security scanners. Packaging, creating the final deployable artifact, e.g., a jar file for Java, a Docker image, an installer, a zip archive of web files. Output, a versioned, tested artifact stored in an artifact repository, ready to be passed to the next stage. Critically, this exact same artifact will be the one that ideally journeys all the way to production, adhering to the build once, deploy many times principle. Key components: build tools, Maven, Gradle, NPM, Yarn, MSBuild, CMake, etc. Static analysis tools, SonarQuebec, EaseLint, CheckStyle, Bandit, etc. Artifact repository, Nexus Artifactory S3 for container images. 4.2.3 Stage 3, test, ensuring quality. This is often the most extensive stage, focusing on verifying the quality and functionality of the software. A well-designed test stage typically involves multiple quality gates. Purpose: to systematically validate the software against requirements and ensure it's free of defects. Actions, increasing in scope and time. Unit tests, automatically executed tests that verify individual components or functions of the code, often run as part of the build stage or at the very beginning of the test stage due to their speed. Integration tests, verify that different components or services within the system interact correctly. Security scans, dynamic application security testing, DAST, tools that test the running application for vulnerabilities, simulating attacks. UI end-to-end tests, automate interactions with the user interface to simulate real user journeys, ensuring the application works correctly from a user's perspective. These are typically slower and run less frequently. Performance load tests, simulate user load to ensure the application performs well under expected and peak conditions. Acceptance tests, verify that the software meets specific business requirements. Output, test reports, coverage reports, and a decision on whether the artifact passes the quality gates and can proceed. Key components, testing frameworks libraries, JUnit, Jest, PyTest, Selenium, Cypress, Playwright, JMeter, etc. Test reporting tools, Allure, Surefire Report, test orchestration, handled by the CI/CD server. Important note, the depth and types of tests run at this stage can be highly customized. Some teams might have separate dev environment tests, staging environment tests, and so on, with artifacts being deployed to specific environments to run those tests. 4.2.4 Stage 4. Deploy, delivering to environments. This is the continuous delivery aspect in full swing. This stage focuses on releasing the validated software artifact to various environments. Purpose: to make the software available in different environments for further testing, demonstration, or ultimately for end users. Actions: environment provisioning, automatically setting up or configuring the necessary infrastructure, servers, databases, network settings for deployment. This is where infrastructure as code, ISC, plays a crucial role, ensuring consistency. Deployment to test staging environments. The artifact is deployed to non-production environments to run further tests, enable user acceptance testing, UAT, or for demonstration purposes by stakeholders. Approval gates. Often, manual approval steps are introduced here before deploying to production, especially in regulated industries or complex systems, defining continuous delivery versus continuous deployment. Deployment to production. The final step, releasing the software to live users. This might involve advanced deployment strategies like canary releases or blue-green deployments to minimize risk and downtime topics for a later chapter. Output, a running instance of the application in the target environment. Key components, CI/CD server, orchestrates the deployment. Deployment tools, Jenkins, Spinnaker, Argo CD, Rundeck, custom scripts. Infrastructure as code, ISC tools, Terraform, Ansible, Chef, Puppet. Container orchestration, Kubernetes, Docker Swarm if using containers. 4.2.5 Stage 5. Monitor the feedback loop. Deployment is not the end of the pipeline. It's a new beginning for continuous feedback. Purpose: to observe the behavior and performance of the deployed application in real time, gather feedback, and identify any issues or opportunities for improvement. Actions: application performance monitoring, APM, collecting metrics on application response times, error rates, resource usage, CPU, memory, and transaction throughput. Logging: centralized collection and analysis of application logs to trace execution flow and debug issues. Alerting: automatically notifying teams if predefined thresholds are breached or critical errors occur. User feedback collection: gathering insights from end users to understand their experience and identify areas for improvement. Output: performance metrics, error logs, user behavior data, and actionable insights that feed back into the source stage, restarting the cycle. Key components, monitoring tools, Prometheus, Grafana, Datadog, New Relic, Splunk. Logging tools, Elk Stack, Elasticsearch, Logstash, Kibana, Splunk, Datadog. Alerting systems, PagerDuty, OpsGenie. 4.3 Pipeline visualization, seeing the flow. One of the great advantages of a CI/CD pipeline is that it makes the software delivery process transparent and visible. Most CI/CD tools provide a visual representation of the pipeline, often as a series of connected boxes or stages. This visualization immediately shows current status. Is the pipeline running? Is it green all stages passed or red a stage failed? Progress. Which stage is the current code change in? Bottlenecks. Which stages take the longest to complete? History. A record of past pipeline runs, their status, and who triggered them. This visibility fosters accountability and allows teams to quickly identify and address issues, whether they are code-related bugs, infrastructure problems, or inefficient processes. 4.4 The benefits of a well-structured pipeline. Having clearly defined stages and automating the transitions between them brings immense value. Predictability and repeatability. Every change goes through the same rigorous process, reducing surprises and ensuring consistent quality. Fast feedback and error detection. Issues are caught early, often within minutes of introduction, making them cheaper and easier to fix. Reduced risk. Smaller, more frequent changes, combined with automated testing and rollback capabilities, significantly lower the risk of deployments. Increased efficiency. Automation frees up developers and operations personnel from tedious, repetitive manual tasks, allowing them to focus on higher-value work. Improved collaboration. A shared, transparent pipeline fosters better communication and collaboration between development, operations, and quality assurance teams. 4.5 Evolving your pipeline. From simple to sophisticated. It's important to remember that a CI/CD pipeline is not a static entity. It should evolve with your team and your software. You might start with a very basic pipeline. Source, build, test, deploy to a single environment. As your confidence grows, you can add more sophistication, more comprehensive testing stages. Deployment to multiple non-production environments with specific purposes, e.g., UAT, performance testing. Automatic security scans. Advanced deployment strategies, e.g., blue, green, canary. Automated environment provisioning infrastructure as code. The key is to start simple, automate what you can, and then continuously iterate and refine your pipeline based on feedback and evolving needs. The pipeline itself becomes a living, breathing component of your software development process, continuously improving and adapting to guide your software through its journey from code to customer with efficiency and reliability. Chapter 5. The Toolkit: Essential Technologies for Your CI/CD Journey. Understanding the principles and the anatomy of a CI/CD pipeline is crucial. Now, let's explore the technologies that make it all possible. The CI/CD ecosystem is vast and constantly evolving, with new tools emerging and existing ones improving. While we won't delve into specific configuration instructions, as these change rapidly and are better found in tool documentation, we will survey the categories of tools that comprise a modern CI/CD pipeline, focusing on their function and role. Remember the constraint: describing functions and roles conceptually, suitable for both print and audio, without code blocks or highly technical snippets. 5.1 The Orchestrators: CI/CD servers and pipeline tools. These are the brains of the operation, the central nervous system that coordinates all other tools and executes the pipeline. They watch your version control system, trigger builds, run tests, and manage deployments. Jenkins: description: an open-source automation server that has been a cornerstone of CI/CD for over a decade, highly extensible through a vast plugin ecosystem. Role: acts as a highly flexible control center. You define jobs or pipelines that specify a sequence of steps, e.g., fetch code, run build tool, execute tests, deploy. Its plugin architecture allows it to integrate with virtually any other tool in the software development lifecycle. Analogy: think of Jenkins as a programmable robot arm in a factory that you can teach to do almost anything by adding different attachments and programming sequences of movements. GitLab CI/CD. Description: integrated CI/CD solution built directly into GitLab, a web-based Git repository manager. Role: provides a seamless end-to-end DevOps platform where source control, CI/CD, security scanning, and other features are all part of the same application. Pipelines are defined in a simple configuration file within the project's repository. Analogy: imagine a self-contained workshop unit where all the necessary tools, the workbench, power tools, measurements, and instructions, are built directly into one cohesive system. GitHub Actions. Description: event-driven automation platform built directly into GitHub, another popular Git repository hosting service. Role: allows developers to automate workflows directly within their repositories for CI, CD, and virtually any other task. Workflows are defined in YAML files and can be triggered by various GitHub events, e.g., code push, pull request, new release. It leverages a concept of actions, which are reusable units of work. Analogy: like a set of Lego bricks, each representing a specific action that you can snap together to build complex automated sequences within your project's repository. Azure DevOps Pipelines. Description: a component of Microsoft's Azure DevOps suite, offering powerful CI/CD capabilities. Role: caters to a broad range of technologies and platforms, supporting cloud-native Azure deployments as well as on-premises environments. It offers both graphical pipeline editors and YAML-based definitions. Analogy: a professional-grade assembly line that can be configured to produce a vast array of tailored products, whether they're destined for a cloud warehouse or a local distribution center. CircleCI/Travis CI/Bitbucket Pipelines. Description: cloud-native CI/CD solutions that integrate deeply with their respective version control platforms. Role: often favored for their simplicity, ease of setup, and scalability, particularly for open-source projects or cloud-centric development. They typically handle infrastructure provisioning for builds and tests automatically. Analogy: cloud-based automated workshops that you can rent on demand, where you bring your plans, and they instantly provide the space and machines to build and test your product without you worrying about the workshop itself. 5.2 The Foundations. Version Control Systems, VCS. The importance of a VCS cannot be overstated. It is the single source of truth for your code and the very first trigger for any CI/CD pipeline. Git. Description: a distributed version control system, by far the most popular in modern software development. Role enables developers to work concurrently, track every change, revert to previous versions, and manage different branches of code. It acts as the repository from which the CI/CD pipeline pulls the source code. Analogy: a constantly updated, perfectly organized library where every single revision of every book is cataloged, and multiple people can work on copies of the same book, merging their changes seamlessly. 5.3 The builders build automation tools. These tools handle the heavy lifting of compiling source code into usable software artifacts. Maven/Gradle, Java. Description: popular build automation and dependency management tools for Java projects. Role: define how a project is built, its dependencies, how tests are run, and how the final deliverable is packaged. The CI/CD pipeline invokes these tools to perform the build stage. Analogy: a highly automated culinary station that knows how to gather all the right ingredients, mix them, bake them, and package the final dish according to a precise recipe. npm/yarn, javascript/node.js. Description: package managers and build tools for JavaScript and Node.js projects. Role: manage project dependencies, run scripts like testing or bundling code, and handle the packaging of web applications or Node.js services. Analogy: a tireless assistant who fetches all the external components your project needs, then executes a series of predefined tasks to get your web application ready for deployment. netcli/msbuild ch/net. Description: command line interfaces and build systems for net applications. Role: compiles net code, manages project dependencies, and constructs deployable packages. The CI/CD pipeline integrates with these to build net applications. Analogy: the master craftsman for net products, who meticulously assembles all components, ensures they fit perfectly, and prepares the final product for distribution. 5.4 The Guardians, testing frameworks and tools. Automated testing is the bedrock of CI/CD, providing the confidence that changes haven't broken existing functionality. JUnit/NUnit/PyTest/just/GoTest. Description: these are representative of various unit testing frameworks across different programming languages. Role: enable developers to write small, fast tests for individual functions or components of their code. These are typically the first line of defense in the CI pipeline. Analogy: tiny, precise inspectors stationed at each workstation of the assembly line, immediately checking if individual components are manufactured perfectly. Selenium/Cypress Playwright. Description: tools for automating web browser interactions, commonly used for UI, user interface, and end-to-end testing. Role: simulate real user behavior in a web application, clicking buttons, filling forms, and verifying that the entire application flows as expected from a user's perspective. These are typically run in later stages of the pipeline due to their longer execution time. Analogy: an automated robot arm that physically sits in front of a computer, mimicking every click and keyboard input a human user would make, meticulously verifying the final product works exactly as intended. JMeter/K6/Locust. Description: performance testing tools that simulate high user loads. Role: help identify how an application behaves under stress, revealing potential bottlenecks or scalability issues before they impact live users. Analogy: a specialized machine that can simulate thousands or millions of users trying to access your product at once to see if your infrastructure can handle the demand without breaking down. 5.5 The Architects. Infrastructure as Code, ISC tools. ISC tools allow you to manage and provision your computing infrastructure through machine-readable definition files, rather than physical hardware configuration or interactive configuration tools. Terraform. Description: an open-source ISC tool that allows you to define and provision infrastructure for any cloud provider or on-premises environment using a declarative configuration language. Role: automates the creation, modification, and destruction of compute instances, networks, databases, and other infrastructure components, ensuring environments are consistent and reproducible for every deployment. Analogy: a master construction blueprint that automatically orders all the necessary building materials and directs robotic cranes to assemble a complex building, ensuring every detail is perfectly matched to the design. Ansible/Chef/Puppet. Description: configuration management tools that automate the setup and configuration of software, services, and operating system settings on servers. Role: once infrastructure is provisioned, these tools ensure that software dependencies are installed, applications are configured correctly, and security policies are applied consistently across all environments. Analogy: a tireless crew of skilled technicians who methodically outfit each newly constructed room with furniture, appliances, and decoration, ensuring every detail matches the interior design specifications. 5.6 The enablers: containerization and orchestration. These technologies have revolutionized how applications are packaged and deployed, ensuring consistency and scalability. Docker. Description: a platform that uses OS-level virtualization to deliver software in packages called containers. Role: packages an application and all its dependencies into a single, portable unit that can run consistently across any environment: developer's laptop, testing server, production data center. It solves the "it works on my machine" problem. Analogy: a standardized shipping container that perfectly seals your entire product along with all its necessary operational instructions, ensuring it opens and functions identically regardless of where it's unloaded. Kubernetes. Description: an open-source system for automating deployment, scaling, and management of containerized applications. Role: manages clusters of machines running Docker containers, handling traffic routing, load balancing, self-healing, and scaling applications up or down based on demand. It streamlines the deployment and operation of complex, distributed applications. Analogy: the sophisticated port management system that perfectly orchestrates the movement of hundreds of shipping containers, knowing exactly where each one needs to go, how to route them, and even repairing them if they get damaged, ensuring continuous flow. 5.7 The watchers. Monitoring and logging tools. Once software is deployed, these tools ensure its health and performance are continuously observed. Prometheus. Grafana. Description: open-source tools for monitoring and data visualization. Prometheus collects metrics from various sources, and Grafana provides rich dashboards. Role: gather real-time performance data, metrics like CPU usage, memory, error rates, network traffic, from your applications and infrastructure. This data is then visualized to give teams immediate insight into operational health. Analogy: a control room with a massive display of live telemetry and gauges, showing the operational status of every critical component of your product as it runs in the field. ElkStack, Elasticsearch, Logstash, Kibana. Splunk. Description: centralized logging and log analysis platforms. Role: collect, store, and analyze application and infrastructure logs from all deployed systems. This allows for quick troubleshooting, root cause analysis, and security auditing. Analogy: an automated and searchable archive that collects every scrap of paper, every conversation, and every functional detail generated by your running product, allowing you to instantly find any piece of information needed for diagnostics. 5.8 The glue. Scripting languages. Beyond dedicated tools, scripting languages are the universal glue that binds different components of the CI/CD pipeline together. Bash/Python PowerShell. Description: general-purpose scripting languages. Role: often used to write custom scripts for specific tasks within the pipeline, automating manual processes, integrating different tools, parsing outputs, or performing pre-post deployment sanity checks. They fill the gaps where a dedicated tool might be overkill or unavailable. Analogy: a versatile handyman with a toolkit full of universal adapters and custom-made connectors, able to make any two disparate machines or systems talk to each other and work in harmony. This comprehensive overview of the CI/CD toolkit demonstrates the breadth of technologies that orchestrate modern software delivery. While the specific brand names may change, the fundamental functionalities they provide remain essential. The key isn't to master every single tool, but to understand what each category contributes to the overall goal: the fast, safe and reliable delivery of high-quality software. Chapter 6. Crafting Quality. Best practices for robust continuous integration. Continuous integration, CI, is the bedrock upon which continuous delivery, CD, is built. A shaky CI foundation will inevitably lead to a fragile and unreliable delivery pipeline. This chapter focuses on the best practices necessary to cultivate a robust and reliable CI process, transforming it from a mere automated task into the true heartbeat of your development efforts. 6.1. The core mantra. Commit early, commit often, commit small. The absolute most fundamental principle of effective continuous integration is the practice of frequent, small commits to the main development line. This directly addresses the integration hell we discussed in Chapter 2. Why it matters. Reduced merge conflicts. When changes are small and integrated frequently, the chances of significant merge conflicts are drastically reduced. If a conflict does occur, it's typically minor and easy to resolve because the change sets are limited. Faster detection of issues. A small commit means fewer variables. If the build breaks after a small change, it's much easier to pinpoint the exact line of code that caused the problem compared to sifting through hundreds of new lines. Consistent mainline. The main branch of your code repository is always kept in a healthy, working state, which means developers are always basing their new work on a stable foundation. Practical application. Instead of working on a complex feature for days and then committing a massive block of code, break it down. Commit after completing a small, verifiable unit of work, even if the feature isn't entirely finished. Think of it as saving your work frequently in a word processor. You don't wait until the entire document is done. 6.2. Automate the build and make it self-testing. The CI server's primary task is to automate the build, but a build isn't complete unless it's fully self-testing. Fast builds are crucial. If your build takes a long time, developers will be discouraged from committing frequently, or they will ignore build failures because waiting for a fix is tedious. Strive for builds that complete in minutes, not hours. Tips for optimization, parallelization, run tests or build steps concurrently. Caching. Store resolved dependencies or build outputs to avoid redundant downloads or recompilations. Incremental builds. Only rebuild parts of the code that have changed. Dedicated build agents. Ensure your CI environment has sufficient processing power and network speed. Comprehensive automated tests. This is where the self-testing part comes in. The quality of your CI process directly correlates with the quality and breadth of your automated test suite. The test pyramid. Envision your tests as a pyramid. Base, many unit tests. Small, fast, inexpensive tests that verify individual units of code, functions, methods. These run very quickly and give immediate feedback. Middle, fewer integration component tests. Verify that different parts of your system work together correctly or that your system integrates with external services. These are slower than unit tests. Top, few end-to-end UI tests. Simulate real user interactions across the entire system, including the user interface. These are the slowest and most brittle but provide confidence in the full user journey. Test quality. Your tests must be reliable, deterministic. They should produce the same result every time given the same input, regardless of when or where they are run. Avoid flaky tests that pass sometimes and fail others without a code change. Fast. The quicker tests run, the more frequently they can be executed, leading to faster feedback. Maintainable. Tests should be easy to understand, update, and debug. Static code analysis. Beyond simply compiling, integrate tools that analyze your code without executing it. Purpose. Catch potential bugs, coding standard violations, stylistic inconsistencies, and even some security vulnerabilities early in the development cycle. Examples: linters for code style, complexity analyzers, security scanners that check for common anti-patterns or insecure coding practices. Warnings from these tools should be treated seriously, not ignored. 6.3. Managing the mainline. Trunk-based development. For optimal CI, the most effective branching strategy is trunk-based development, TBD. This is where all developers commit directly to a single main branch, often called trunk or main, multiple times a day. How it works. Instead of long-lived feature branches that diverge far from the main code, developers work on short-lived branches, maybe a few hours or a day, or even directly on the main line for very small changes. They integrate their small changes frequently back into the main branch. Contrast with long-lived feature branches. While feature branches have their place, relying on them for core development can lead to accumulated integration debt. If a branch lives for weeks or months, merging it back into the main line becomes a significant, risky event, undermining the continuous nature of CI. Enabling TBD with feature flags. Sometimes, a large feature cannot be delivered in tiny, isolated commits. Feature flags, or feature toggles, offer a solution. A feature flag is a technique that allows you to turn features on or off without deploying new code. This means you can commit incomplete features to the main branch behind a flag, keeping them disabled for users. Once the feature is complete and thoroughly tested, you simply flip the flag to turn it on for users. This allows for continuous integration while enabling complex feature development. 6.4, the cardinal rule: fix broken builds immediately. This is arguably the most critical rule for CI. If the build breaks, all development work should halt until the issue is resolved. Why it's critical? A broken build means the main branch is unstable. If new code is committed on top of a broken build, it compounds the problem, making it far more difficult to diagnose the original cause and leading to build decay. A team that tolerates broken builds is not truly practicing CI. Practical strategies: assign responsibility. Clearly define who is responsible for fixing a broken build immediately, e.g., the person who broke it, the last person to commit, a rotating build captain. Visible alarms. Make build failure impossible to ignore. Use loud notifications, audio alarms, visible build status lights or monitors, and team chat alerts. Prioritize fixes. Fixing a broken build takes precedence over any other development task. Revert if necessary. If a fix isn't immediately obvious, don't hesitate to revert the problematic commit, get the build green, and then attempt the fix in a new, separate commit. 6.5, visibility and feedback. Making the pipeline transparent. A CI process is only effective if its status is clear and accessible to everyone on the team. Dashboards and build monitors. Display the status of the main pipeline prominently in the team's workspace, e.g., a TV screen. Green indicates a healthy build, red means trouble. Notifications. Configure your CI server to send automated notifications to the relevant team chat channels, email lists, or individual developers when a build status changes, especially on failure or recovery. Comprehensive reports. Ensure test reports, static analysis findings, and build logs are easily accessible and understandable. This helps developers learn from failures and improve their code. Fast feedback loops. The entire CI process, from commit to feedback, should be as fast as possible. This allows developers to stay in a flow state and makes fixing issues less disruptive. 6.6, reproducibility. Identical builds every time. Every time the CI pipeline runs, it should produce the exact same output artifact, if given the same input, source code, and dependencies. Dependency management. Rigorously manage all project dependencies, making sure specific versions are locked down. Avoid relying on latest versions, which can change unexpectedly. Clean build environment. Always build in a clean, consistent, and isolated environment. Avoid using the same build agent for multiple concurrent jobs that might interfere with each other or carry over leftover files. Containerization. Using technologies like Docker, as discussed in Chapter 5, for your build environment is an excellent way to ensure reproducibility. You can define a Docker image that contains all the necessary tools and dependencies for your build. Every time the pipeline runs, it launches a fresh container from this image, ensuring a consistent environment. 6.7, clean build environment. Building on reproducibility, maintaining a pristine build environment prevents subtle, difficult-to-diagnose issues. Dedicated build infrastructure. Do not use developers' workstations as build servers. Use dedicated, controlled infrastructure. Disposability. Ideally, build environments should be treated as disposable. They are spun up for a build used and then destroyed or completely reset. This prevents snowflaking, where minor, undocumented changes build up on a machine, leading to inconsistent build results. Centralized tooling. Ensure all necessary build tools, compilers, and SDKs are centrally managed and consistently configured across all build agents. Crafting a robust continuous integration process requires discipline, automation, and a commitment to quality from every team member. By adhering to these best practices, committing small and often, ensuring fast and comprehensive automated tests, prioritizing immediate fixes for broken builds, and maintaining clear visibility teams can foster a continuously healthy and stable codebase, laying the essential groundwork for smooth and reliable continuous delivery. Chapter 7, Deployment Done Right, Strategies for Resilient Continuous Delivery. Having mastered continuous integration and established a robust CI pipeline, the next critical step is to ensure that your thoroughly tested software can be deployed reliably, safely, and frequently. This chapter delves into the strategies and considerations for building resilient continuous delivery (CD) practices, turning deployments from stressful events into routine operations. 7.1 Automating the Last Mile. Beyond the build. In continuous delivery, the goal is to make deployment an automated, repeatable, and low-risk process. This means scripting every step involved in getting your application from its artifact form to a running state in a target environment. Script everything. Every action, from provisioning infrastructure to installing dependencies, configuring services, and starting the application, should be expressed as code. This eliminates human error, ensures consistency, and allows for rapid execution. Idempotence. Your deployment script should be idempotent. This means running the script multiple times should have the same effect as running it once. For example, if a script checks if a service is running and starts it if not, and performs no action if it is already running, it's idempotent. This is crucial for retries and recovering from partial failures. No manual intervention. Once a deployment pipeline starts, there should be no need for manual steps. Any human decision, like go to production, should be an explicit gate that triggers the next automated step, not a signal for a human to start typing commands. 7.2 Consistent Environments. The build once, deploy many times principle. A cornerstone of resilient continuous delivery is ensuring that the software behaves identically across all environments, from development to production. The principle of build once, deploy many times is central here. The exact same artifact that passed tests in the CI environment should then traverse the entire CD pipeline. Identical environments. Strive to make your test, staging, and production environments as identical as possible. This minimizes the "it works on my machine" or "it works in staging" syndrome. Discrepancies in operating system versions, library versions, network configurations, or environment variables can lead to subtle, hard-to-debug failures. Infrastructure as code (ISC). This is paramount for achieving environment consistency. Instead of manually configuring servers, use ISC tools like Terraform, CloudFormation, Ansible, Chef, Puppet, as discussed in Chapter 5, to define your infrastructure programmatically. Benefits of ISC. Version control. Your infrastructure is defined in code, which can be stored in your VCS, allowing for history tracking, collaboration, and easy rollback. Reproducibility. You can recreate environments consistently and on demand, e.g., for new feature development, testing, or disaster recovery. Automation. ISC tools automate the provisioning and configuration processes, eliminating manual errors. Containerization. Technologies like Docker significantly aid in achieving environment consistency by packaging your application and all its dependencies into a single, portable unit. Benefits of containers. Isolation. Applications run in isolated environments, preventing conflicts between different applications or dependencies. Portability. A Docker image that runs on a developer's laptop will run identically on a staging server or in production. Efficiency. Containers are lightweight and start quickly, making them ideal for dynamic environments. Environment management and disposal. Treat environments as disposable. When a new feature branch starts, spin up a dedicated test environment for it. After the feature is merged and deployed, tear down that environment. This ensures cleanliness and reduces environment drift and cost. 7.3 Release Strategies. Minimizing risk and downtime. The final step of deploying to production can still be nerve-wracking. Modern CD practices employ sophisticated release strategies to minimize risk, reduce downtime, and provide rapid rollback capabilities. 1. Recreate deployment, downtime expected. How it works. Shut down the old version, deploy the new version, then start the new version. Pros: simple, easy to understand. Cons: involves downtime, which might be unacceptable for many applications. Use cases: non-critical internal tools, applications where scheduled downtime is acceptable. 2. Rolling deployment, phased rollout. How it works. Replace instances of the old version with new instances one by one or in small batches over a period of time. This maintains service availability during the upgrade. Pros: no downtime, easy to implement with container orchestrators like Kubernetes. Cons: can have a mixed environment, old and new versions running simultaneously, potential for issues if backward compatibility is broken. Rollback can be complex if many instances have been updated. Use cases: most web applications, microservices. 3. Blue-green deployment. How it works. Maintain 2 identical production environments. Blue, the current live version, and green, the new version. Deploy and test the new version in the green environment. Once happy, all incoming traffic is switched from blue to green. The blue environment is kept as a warm standby for quick rollback, or can be used for the next deployment. Pros: zero downtime, instant rollback, just switch traffic back to blue, high confidence in the new version as it's fully warmed up and tested in a production-like setting. Cons: twice the infrastructure cost, at least temporarily, more complex to set up. Analogy: imagine a busy highway. Instead of stopping traffic to resurface one lane at a time, you build an entirely new, identical highway next to it, then divert all traffic to the new highway once it's ready. If there's a problem, you just divert back to the old one. 4. Canary release. How it works. A new version is deployed to a small subset of users, the canaries or servers, in a phased manner. Closely monitor this small group for errors or performance issues. If stable, gradually roll out to more user servers. If issues arise, roll back the small group. Pros: reduces risk by exposing new code to a limited audience first, real-world testing. Excellent for A/B testing new features. Cons: more complex to set up and manage, requires robust monitoring to detect issues in the canary group quickly. Analogy: inspired by miners using canaries in coal mines. If the canary stopped singing, it indicated dangerous gases, warning the miners before it was too late. Here, a small group of users acts as the canary. 5. Dark launching/feature flags. How it works. Deploy new code to production, but keep its features disabled or hidden from users using feature flags, also known as feature toggles. This allows for testing in production without impacting users. Then, features can be selectively enabled for specific users or groups. Pros: decouples deployment from release, features can be tested in a live environment, quick rollback by simply toggling the feature off. Cons: requires careful management of feature flags, can increase code complexity if not managed well. Use cases: gradual rollout of new features, A/B testing, testing risky changes in production with zero user impact. The choice of deployment strategy depends on your application's criticality, acceptable downtime, infrastructure, and risk tolerance. Most modern CD pipelines will use a combination of these strategies. 7.4 Robust rollback capabilities. No matter how good your testing and deployment strategies are, problems can still occur in production. The ability to quickly and safely revert to a previous stable version is paramount for resilient CD. Automated rollback. Just as deployments are automated, so too should be rollbacks. Your CD pipeline should have a clear, automated path to revert a deployment. Speed. Rollbacks must be fast. The longer a faulty version runs in production, the greater the impact. Pre-existing artifacts. This is where artifact management, from Chapter 2, is crucial. Ensure that previous stable artifacts are readily available for quick redeployment. Consider data migration. Rollbacks can be complex when database schema changes are involved. Plan data migrations carefully, ensuring they are backward compatible or designing for graceful degradation if a rollback occurs. 7.5 Beyond deployment, post-deployment verification. A deployment is not truly complete until you've verified that the new version is working correctly in production. This post-deployment verification should also be automated as part of your CD pipeline. Smoke tests. Run a small suite of critical, fast tests against the newly deployed application in production. These are not meant to be comprehensive, but rather to ensure the application has started successfully and basic functionality is intact. Health checks. Configure your application to expose health endpoints that the monitoring system can regularly query. Synthetic monitoring. Use external services to simulate user interactions from various locations, ensuring your application is reachable and responsive from the outside world. 7.6 Continuous monitoring. The feedback loop in action. As discussed previously, continuous monitoring is the final stage of the pipeline, but it's also the first step of the next iteration. Real-time observability. Utilize monitoring tools, e.g., Prometheus, Grafana, Splunk, Datadog, to gather metrics, logs, and traces from your deployed application. Understand its performance, resource utilization, and error rates. Alerting. Set up alerts for critical thresholds or anomalies. If CPU usage spikes, error rates increase, or response times degrade, the relevant teams should be notified immediately. Impact analysis. Be able to quickly correlate changes with production issues. If a deployment occurred at 10:00 a.m. and errors started at 10:05 a.m., it's highly probable the deployment caused the problem. Business metrics. Monitor not just technical performance, but also business-critical metrics. Is the new feature increasing conversion rates? Is it affecting user engagement? This helps validate the value delivered by your software. Resilient continuous delivery transforms software releases from high-stakes events into a safe, reliable, and routine process. By automating thoroughly, striving for environmental consistency, adopting intelligent deployment strategies, ensuring robust rollback capabilities, and maintaining continuous vigilance through monitoring, organizations can deliver value to their users with unprecedented speed and confidence. This paves the way for further advancements, such as integrating security and enabling rapid iteration based on real-world feedback. Chapter 8, Quality First. Integrating testing into every stage of CI/CD. In the world of continuous integration and continuous delivery, quality is not an afterthought. It's a prerequisite. Testing is not a separate phase performed at the end of the development cycle by a dedicated quality assurance (QA) team. Instead, automated testing is deeply embedded into every stage of the CI/CD pipeline, providing rapid and continuous feedback. This approach, often summarized as shifting left, ensures that quality is built in from the start, rather than patched on at the end. 8.1 The shift left philosophy, catching bugs early. Traditionally, testing was a sequential process. Development completed, then code was handed off to QA for testing. Any bugs found at this late stage were expensive and time-consuming to fix. Imagine finding a major design flaw in a new car model just as it's about to roll off the assembly line. It's infinitely cheaper and easier to fix that flaw during the design phase. Shifting left means moving quality assurance activities and testing closer to the initial stages of the software development lifecycle. In the context of CI/CD, this translates to developers writing tests. Developers don't just write code, they write tests, unit, integration for their code. Automated execution. These tests are automatically executed with every small code change, providing immediate feedback. Early feedback. Issues are discovered within minutes or hours, rather than days, weeks, or months. This immediate feedback loop is the magic of CI/CD. It allows for quick course correction, preventing small issues from snowballing into critical problems. 8.2 The Test Automation Pyramid Revisited. We touched upon the testing pyramid in Chapter 6. It's so fundamental to CI/CD that it warrants a deeper dive here. The pyramid illustrates the ideal distribution of different types of automated tests. Many unit tests, base of the pyramid, Focus, testing the smallest individual components or functions of your code in isolation. Characteristics, fast to write, fast to execute milliseconds, provide very precise feedback on where a bug is located and mock external dependencies. Integration in CI/CD, run with every code commit, typically as part of the build stage or the very beginning of the test stage. They are the first line of defense. Quality gate, if unit tests fail, the build is immediately broken and the developer responsible is notified. Code does not proceed. Fewer integration tests, middle layer. Focus, verifying that different modules or services within your application correctly interact with each other or with external systems, databases, APIs, message queues. Characteristics, slower than unit tests, may require some setup of external dependencies, either real or simulated. Integration in CI/CD, run after unit tests, usually as part of the test stage. Quality gate, failure here indicates a problem in how components integrate, preventing deployment to further environments. Even fewer UI/end-to-end tests, top layer. Focus, simulating a user's journey through the entire application, interacting with the user interface from start to finish. Characteristics, slowest to execute, seconds to minutes, most fragile, prone to breaking with minor UI changes, and most expensive to maintain. They often require a browser or a full client environment. Integration in CI/CD, typically run in a dedicated test environment, like staging after successful lower-level tests, perhaps less frequently than unit integration tests due to their execution time. Quality gate, confirm that the complete system delivers the expected user experience. Why a pyramid, not an ice cream cone? Many E2E tests. Speed, running too many slow, fragile end-to-end tests frequently will make your pipeline painfully slow, negating the continuous aspect. Feedback, if an end-to-end test fails, it's harder to pinpoint the exact root cause compared to a failing unit test. Cost, end-to-end tests are more complex to write and maintain. The goal is to catch as many defects as possible with the fastest, cheapest tests, unit tests, at the bottom of the pyramid. Only rely on the slower, more expensive tests at the top for what they are best suited for, verifying overall system behavior and user experience. 8.3 Beyond functional tests, a holistic view of quality. Quality in CI/CD extends beyond just whether the application works. It encompasses reliability, performance, security, and usability. The pipeline should incorporate various types of automated checks throughout its stages. 1. Static application security testing, SAST. What it is: analyzing source code, bytecode, or binary code for security vulnerabilities without executing the code. When to run, preferably in the build stage or early test stage. Why it's important: catches common vulnerabilities, e.g., SQL injection, cross-site scripting, early in the development cycle, before they even reach a running application. 2. Dynamic application security testing, DAST. What it is: analyzing a running application from the outside, simulating attacks to find vulnerabilities. When to run: in a dedicated test environment, e.g., staging, once the application is deployed and runnable. Why it's important: identifies vulnerabilities that might only appear when the application is running in its operational environment. 3. Performance testing, load, stress, scalability. What it is: simulating user load to assess how the application behaves under various conditions. When to run: in a dedicated test or staging environment, usually after functional tests pass. Why it's important: ensures the application meets performance requirements, handles expected user traffic, and scales efficiently. Failure here can prevent costly and reputation-damaging outages in production. 4. Accessibility testing. What it is: ensuring your application is usable by people with disabilities, e.g., visual impairments, motor difficulties. Automated tools can check for common accessibility violations. When to run: can be integrated into UI testing frameworks or run as separate checks in the test stage. 5. Contract testing. What it is: verifying that two services, e.g., a front-end and a back-end API, adhere to a shared agreement contract about how they will communicate, preventing breaking changes between independent teams. When to run: can be part of the build or test stage for each service. Why it's important. Essential for microservices architectures where many independent services need to interact reliably. 8.4 Building testable code. Effective test automation isn't just about deploying tools, it's about writing code that is designed to be easily tested. Single Responsibility Principle, SRP. Write small, focused components or functions that do one thing and do it well. This makes them easier to test in isolation. Dependency injection. Design your code so that its dependencies, e.g., external services, databases, can be easily swapped out with mocks or stubs during testing. This allows you to test a component in isolation without needing a fully running version of all its dependencies. Clear interfaces. Define clear interfaces for your modules and services. This helps in understanding their behavior and makes it easier to write tests that interact with them. Avoid global state. Global variables or mutable shared state can make tests flaky and unpredictable. Prefer local variable and passing data explicitly. Readable code. Clean, well-structured, and readable code is not only easier to maintain, but also easier to test. 8.5 Test, data management, and environment strategy. Tests need data, and environments need to be consistent. Realistic test data. Use test data that is as close to production data as possible, while ensuring privacy and security. This helps uncover issues that might only appear with specific data characteristics. Automated data provisioning. Automate the creation and cleanup of test data for your environments. This ensures tests are repeatable and don't interfere with each other. Dedicated test environments. Have dedicated environments for different types of tests, e.g., a performance test environment. Ephemeral environments. Leverage containerization and ISC to spin up and tear down temporary environments for specific test runs, e.g., for feature branches or pull requests, ensuring isolation and preventing interference. 8.6 Measuring test effectiveness. It's not enough to just run tests, you need to know if they're actually effective. Code coverage, what it is. A metric that measures the percentage of your source code that is executed by your tests. Purpose, while not a guarantee of quality, 100% coverage doesn't mean zero bugs, it's a good indicator of untested code. Aim for high code coverage, especially for unit tests. Caveat: don't chase 100% coverage blindly. Focus on testing critical paths and complex logic. Test results visibility. Integrate test results directly into your CI/CD pipeline's dashboard. Instantly see which tests passed, which failed, and why. Failure analysis. When tests fail, investigate immediately. Identify the root cause, fix the code, and ideally, add a new test case to prevent the same bug from recurring. Flaky test management. Flaky tests, tests that pass and fail randomly without actual code changes, erode trust in the build. Identify and fix or quarantine flaky tests immediately. Don't let them be ignored. Integrating automated testing effectively throughout your CI/CD pipeline is the single most powerful way to build quality in from the ground up. It transforms quality assurance activities from a bottleneck at the end of the process into continuous, rapid feedback loops that empower developers, increase confidence, and ultimately deliver higher quality software to delighted users. Chapter 9, The Feedback Loop, Monitoring, Metrics, and Continuous Improvement. The journey of continuous delivery doesn't end when your software is successfully deployed to production. In fact, deployment marks just the beginning of another crucial phase: observation, learning, and continuous improvement. This is where the feedback loop truly comes into its own, transforming raw data into actionable insights that drive future development and refine the CI/CD pipeline itself. 9.1 The Importance of Observability. Once your application is live, you need to understand how it's performing, how users are interacting with it, and detect any issues as soon as they arise. This is where observability comes in. Observability is the ability to infer the internal state of a system by examining its external outputs. It allows you to ask arbitrary questions about your system's behavior without knowing beforehand what you might need to ask. Traditional monitoring focuses on predefined metrics and known failure modes, e.g., is CPU over 80%? Observability goes deeper, providing the tools to explore and understand why something is happening, even for novel, unforeseen issues. The three pillars of observability are often cited as metrics, numerical values representing aspects of your system at a given time, e.g., CPU utilization, request latency, error rates. Logs, time-stamped records of events that occurred within your application or infrastructure, e.g., user login, error messages, database queries. Traces, end-to-end views of requests as they flow through distributed systems, showing how different components interact to fulfill a single user action. Effective monitoring and a strong focus on observability are not just about finding bugs. They are about understanding the actual impact of your changes on users and the business. 9.2 Key metrics to monitor. To truly understand your system's health and performance, you need to collect and visualize a range of metrics. Metrics can be broadly categorized as follows. System infrastructure metrics. CPU utilization, how much processing power is being used. Memory usage, is there enough RAM available? Are there memory leaks? Disk I/O, how actively is the system reading from or writing to disk? Network throughput, how much data is being sent and received? Latency, the delay between a request and a response for specific services or APIs. Queue lengths, for message queues, how many messages are waiting? Application-specific metrics, business and performance. Error rates, percentage of failed requests, distinguishing between client errors, 4xx, and server errors, 5xx. Request per second RPS. Throughput, how many requests is the application handling? Is it processing expected volumes? Response times, latency. How long does it take for the application to respond to user requests, often measured in percentiles, e.g., 99th percentile response time? Active user sessions, how many users are currently interacting with the application? Conversion rates, for business-critical applications, are users completing desired actions, e.g., purchases, sign-ups? Feature usage, which new features are being adopted and used, and by whom? This is especially important when using feature flags. Resource consumption per request, understanding the cost footprint of individual operations. 9.3 Centralized logging and analysis. Applications generate vast amounts of log data. Centralized logging is vital for making sense of this information. Aggregation. All logs from various application instances, servers, and services should be collected and sent to a central logging system. Structured logging. Instead of plain text, encourage structured log formats, e.g., JSON. This makes logs easier to parse, query, and analyze programmatically. Search and analysis. Use powerful logging tools like the Elk Stack, Elasticsearch, Logstash, Kibana, or Splunk to search, filter, and analyze log data efficiently. This allows you to quickly pinpoint errors, trace user flows, and identify patterns. Alerting from logs. Set up alerts based on specific log patterns, e.g., too many fatal error messages in a given time frame. 9.4 Tracing for distributed systems. As applications evolve into microservices architectures, a single user request might traverse multiple services, databases, and external APIs. This makes debugging complex. Distributed tracing provides visibility into these interactions. How it works. Each request is assigned a unique identifier that is propagated across all services it touches. Tracing tools then allow you to visualize the entire path of a request, showing which services were called, how long each call took, and where errors occurred. Benefits. Crucial for pinpointing performance bottlenecks and understanding the root cause of issues in complex, distributed environments. 9.5 Alerting and on-call rotation. Monitoring is passive. Alerting is active. When metrics cross predefined thresholds or logs show critical events, the right people need to be notified immediately. Contextual alerts. Alerts should be actionable and provide enough context for the recipient to understand the problem quickly. Avoid noisy alerts that result in alert fatigue. Clear runbooks/playbooks. For every critical alert, there should be a clear, documented procedure, a runbook or playbook, on how to investigate and resolve the issue. On-call rotation. Establish a clear on-call rotation so that a designated team member is always available to respond to critical alerts. This often involves tools like PagerDuty or OpsGenie. Blameless postmortems. When an incident occurs, conduct a thorough, blameless postmortem analysis. Focus on understanding the systemic causes of the problem rather than assigning blame. The goal is to learn from failures and prevent reoccurrence. 9.6. Building the feedback loop into the pipeline. The insights gained from monitoring and observability don't just stay in a dashboard. They must feed back into the CI/CD pipeline and the development process itself. Automated rollback triggers. If monitoring detects a critical issue immediately after a deployment, the pipeline should be able to automatically trigger a rollback to the previous stable version. This is the ultimate automated feedback. Performance baselines as gates. Integrate performance testing into your pipeline. Compare new releases against performance baselines. If a new version introduces performance regressions, the pipeline should block deployment. A/B testing and canary metrics. When using A/B testing or canary deployments, monitor business metrics, e.g., conversion rates, user engagement, closely. The pipeline might automatically roll back or promote the new version based on predefined success or failure criteria for these metrics. DevOps culture. The continuous feedback loop fosters a strong DevOps culture. Developers gain ownership of their code in production and learn directly from its performance and user interactions. Operations teams provide valuable insights that directly influence development priorities. 9.7. Continuous improvement. The always-on mindset. The feedback loop isn't just for immediate incident response. It's the engine for continuous improvement across the entire software delivery lifecycle. Reviewing CI/CD metrics. Build success rate, percentage of successful CI builds. A low percentage indicates problems in integration or testing. Deployment frequency. How often are you deploying to production? Higher frequency generally indicates faster delivery of value. Lead time for changes. The time it takes for a change to get from committed code to running in production. A key metric for agility. Change failure rate. Percentage of deployments that result in service degradation or require rollback. A low rate indicates high quality. Mean time to recovery, MTTR. The average time it takes to restore service after an outage. Sprint reviews and retrospectives. Regularly discuss monitoring data, incident reports, and pipeline metrics in team meetings. Identify bottlenecks, areas for automation, and opportunities to improve code quality. Kaizen, continuous improvement. Embrace the philosophy of small, incremental, positive changes. Constantly ask, how can we make our tests faster? How can we make our deployments more reliable? How can our monitoring give us better insights? How can we reduce manual steps? Experimentation. Use your CI/CD pipeline as a platform for experimentation. Rapidly test new technologies, architectural changes, or process improvements. By diligently applying monitoring and metrics and closing the feedback loop, organizations can move beyond simply delivering software to continuously learning from their systems in production, iteratively improving both the product and the process itself. This mindset is key to staying competitive and innovative in a rapidly changing technological landscape. Chapter 10. Securing the pipeline. Integrating security into CI/CD, DevSecOps. In the past, security was often a bottleneck in the software delivery process. Security reviews were typically conducted as a separate, late-stage gate, often called security theater, because real issues were usually found too late to fix easily, leading to delays and compromises. This security-last approach is fundamentally incompatible with the speed and agility of CI/CD. The modern approach, known as DevSecOps, advocates for integrating security practices and considerations throughout the entire CI/CD pipeline and across the full software development lifecycle. It's about shifting security left, embedding security controls and awareness at every stage, from initial design to deployment and continuous monitoring. The goal is to make security a shared responsibility, not just the domain of a separate team. 10.1. Why shift security left? The imperative of DevSecOps. The reasons for integrating security early and continuously are compelling. Cost efficiency. finding and fixing vulnerabilities earlier in the development lifecycle is exponentially cheaper than finding them in production. A bug found during coding might cost dollars to fix, during testing hundreds, but in production, it can cost thousands or millions in terms of remediation, reputation damage, and lost customer trust. Speed and agility. Late-stage security reviews create bottlenecks. By automating security checks and making them part of the regular CI/CD flow, you maintain velocity without sacrificing security. Reduced risk. Proactive security practices lead to fewer vulnerabilities making it to production, significantly lowering the risk of data breaches, compliance violations, and system compromises. Shared responsibility. DevSecOps fosters a culture where developers, operations, and security teams collaborate, understanding that security is everyone's job. This leads to informed decision-making and better secure coding practices. Compliance and governance. Many regulations, e.g., GDPR, HIPAA, PCI DSS, require robust security controls and auditable processes, which DevSecOps helps facilitate. 10.2. Integrating security into each stage of the CI/CD pipeline. Let's explore how security can be woven into the fabric of your CI/CD pipeline, mirroring the stages discussed in Chapter 4. 10.2.1 Design and Plan, Pre-Pipeline. Even before coding begins, security considerations should be paramount. Threat modeling. Systematically identify potential threats and vulnerabilities in the application's design. This involves mapping out the application's architecture, identifying data flows, and brainstorming potential attack vectors. Security requirements. Define security requirements explicitly, just like functional requirements. Secure coding guidelines. Establish and communicate secure coding best practices to developers. Security training. Provide regular security awareness and secure coding training for all development teams. 10.2.2 Source. Code development and version control. Security begins with the code itself. Secure coding practices. Developers are trained to write secure code from the outset, considering common vulnerabilities. Secrets management. Never hardcode sensitive information, API keys, database passwords, directly into source code. Use dedicated secrets management tools, e.g., HashiCorp Vault, AWS Secrets Manager, Azure Key Vault, that integrate with the CI/CD pipeline to inject secrets securely at runtime. Version control security. Ensure strict access controls on your version control system, require multi-factor authentication, MFA, and regularly audit repository access. 10.2.3 Build, compile, and package. Automated security checks should integrate with the build process. Static application security testing, SAST. Tools like SonarQuebec, Checkmarks, Fortify Static Code Analyzer, analyze source code for common security vulnerabilities, e.g., SQL injection, buffer overflows, insecure configurations, without executing the application. These checks should run as non-blocking, initially, or blocking gates within the CI pipeline. Dependency scanning, software composition analysis, SCA. Tools identify known vulnerabilities in third-party libraries and open-source components that your application uses. Most applications rely heavily on external dependencies. Vulnerabilities in these components are a significant attack surface. Container image scanning. If you're building Docker images, scan them for vulnerabilities in the base image, operating system packages, and application layers. This ensures that the container itself is secure before deployment. 10.2.4 Test, automated and manual quality gates. Leverage testing, stages to dig deeper for security flaws. Dynamic application security testing, DAST. Tools like OWASP Zap, Burp Suite, Akunatics test the running application for vulnerabilities by simulating attacks and analyzing responses. This is complementary to SAST, as DAST can find issues related to runtime configuration, authentication, and session management. API security testing. Automated tests that specifically target your APIs for vulnerabilities, ensuring proper authentication, authorization, input validation, and rate limiting. Fuzz testing. Providing malformed or unexpected input to an application to uncover crashes or vulnerabilities. Integrate security into functional tests. Ensure that your automated functional tests also include negative test cases designed to break security controls, e.g., attempting to bypass authentication, accessing unauthorized data. Penetration testing, manual during later stages. While automation is key, human-led penetration tests, or bug bounty programs, provide an invaluable layer of security testing that automation cannot fully replicate. These are typically performed on staging or pre-production environments. 10.2.5 Deploy, release to environments. Ensure secure deployment practices and environment hardening. Infrastructure as code, ISC security scanning. Lint and scan your ISC templates, e.g., Terraform, CloudFormation, for security misconfigurations before provisioning infrastructure. Tools can detect unencrypted storage, publicly exposed ports, or weak access policies. Immutable infrastructure. Build new environments for each deployment rather than updating existing ones. This reduces configuration drift and ensures a clean, predictable state. Secrets injection. Only inject necessary secrets into the runtime environment at deployment time, using secure mechanisms, e.g., environment variables, mounted volumes from secrets managers, ensuring they are not exposed in logs or build artifacts. Least privilege. Configure networks, roles, and service accounts with the principle of least privilege, granting only the minimum permissions necessary for the application to function. Secure configuration management. Automate the secure configuration of servers, firewalls, and application settings. 10.2.6 Monitor, post-deployment and production. Security vigilance continues long after deployment. Continuous monitoring. Monitor for security events, anomalies, and potential attacks in real time. This includes security information and event management, SIEM, tools that collect and analyze security logs from various sources to detect suspicious activity. Intrusion detection prevention systems, IDS/IPS, network-level monitoring for malicious traffic patterns. Web application firewalls, WAF, protect web applications from common web-based attacks. Cloud security posture management, CSPM, continuously monitor cloud configurations for security compliance and misconfigurations. Anomaly detection. Use machine learning to detect unusual user behavior or system patterns that might indicate a compromise. Incident response. Have a well-defined and regularly practiced incident response plan for when a security breach occurs. Vulnerability management. Continuously scan production systems for patch levels and new vulnerabilities. 10.3 Culture and collaboration in DevSecOps. Ultimately, DevSecOps is a cultural journey, not just a technical one. Security champions. Designate individuals within development teams to be security champions. These individuals act as local experts, promoting secure coding practices and liaising with the central security team. Training and awareness. Regular, practical security training for developers, specific to the technologies they use. Collaboration. Foster open communication and collaboration between development, operations, and security teams. Break down silos. Gamification. Use bug bounty programs or security-focused hackathons to engage developers and make security fun. Metrics that matter. Track security metrics across the pipeline, e.g., number of vulnerabilities found per build, time to remediate critical vulnerabilities, security test coverage, and integrate them into team performance goals. By embedding security disciplines throughout the CI/CD pipeline, organizations can achieve a mature DevSecOps posture. This transforms security from a reactive bottleneck to a proactive enabler, allowing teams to deliver secure software at the speed and scale demanded by modern business, providing a robust defense against ever-evolving cyber threats. Chapter 11, CI/CD in Context, Adapting to Microservices, Cloud, and Legacy Systems. The principles of continuous integration and continuous delivery are universal, but their implementation can vary significantly depending on the architectural landscape you're navigating. Modern software often lives in complex environments, from highly distributed microservices to cloud-native deployments, and sometimes alongside monolithic legacy systems. This chapter explores how CI/CD adapts to these diverse contexts. 11.1 CI/CD and microservices, orchestrating distributed systems. Microservices architecture, characterized by small, independent services that communicate via APIs, presents both opportunities and complexities for CI/CD. Opportunities: independent deployment. Each microservice can have its own independent CI/CD pipeline. This means teams can develop, test, and deploy their services without waiting for or affecting other teams, leading to faster delivery cycles for individual services. Technology heterogeneity. Different microservices can use different technologies, programming languages, and frameworks, each with its optimized CI/CD toolchain. Faster rollbacks. If an issue is found in one microservice, only that service needs to be rolled back, limiting the blast radius compared to a monolithic application. Complexities and adaptations. Pipeline sprawl. Managing dozens or hundreds of independent CI/CD pipelines can become complex. Centralized dashboards and consistent pipeline templates become crucial. Distributed testing. How do you test the integration of multiple microservices? Consumer-driven contracts, CDC. This is a key practice. Instead of traditional integration tests across many services, each service defines contracts, agreements on how it communicates that consumers' other services rely on. Both provider and consumer run automated tests against these contracts, ensuring compatibility without needing to spin up entire environments. Service virtualization, simulating the behavior of dependent services during testing. Deployment coordination. While services are deployed independently, sometimes a new feature requires changes across multiple services. How do you coordinate the deployment order or ensure compatibility? Advanced routing, like API gateways and robust monitoring, tracing become essential. Observability. Understanding the flow of a request across many services requires sophisticated distributed tracing and centralized logging. Release management. Tools that visualize and manage releases across multiple interdependent services become important. Key CI/CD tools for microservices. Containerization, Docker, and orchestration, Kubernetes. Essential for packaging, deploying, and managing microservices consistently across environments. Kubernetes, in particular, offers powerful features for rolling updates, self-healing, and service discovery. Service meshes, e.g. Istio Linkerd, provide capabilities for traffic management, security, and observability between services without changing the application code. They can simplify A/B testing and canary releases for microservices. 11.2 CI/CD on the cloud, leveraging cloud-native capabilities. Cloud platforms Oz, Azure, Google Cloud are natural homes for CI/CD, offering on-demand infrastructure, managed services, and powerful native tools. Opportunities, scalability. Cloud CI/CD services can automatically scale to handle varying build and deployment demands, eliminating infrastructure procurement bottlenecks. Managed services. Cloud providers offer managed versions of essential CI/CD components, e.g., build services, container registries, artifact repositories, secrets managers, reducing operational overhead. Global reach. Deployments can target multiple geographic regions easily for improved resilience and performance. Serverless computing. CI/CD can deploy serverless functions, e.g., AWS Lambda, Azure Functions, focusing purely on code without managing servers. High availability and disaster recovery. Cloud environments simplify building redundant and geographically distributed CI/CD pipelines. Complexities and adaptations. Vendor lock-in, potential. Over-reliance on proprietary cloud CI/CD features might make migration to another cloud provider challenging. Balance convenience with portability. Cost management. While cloud is elastic, inefficient resource use within CI/CD pipelines can lead to unexpected costs. Optimize build times and resource allocation. Security. Properly configuring cloud security policies, identity and access management, IAM, for CI/CD pipelines is paramount to prevent unauthorized access to resources and code. Cloud-specific ISC. CloudFormation, AWS, ARM templates Azure, and Google Cloud Deployment Manager are cloud-native ISC tools that integrate deeply with their respective clouds. Key CI/CD tools on the cloud. Cloud-native CI/CD services. AWS Code Pipeline Code Build Code Deploy, Azure DevOps Pipelines, Google Cloud Build. These offer deep integration with their respective cloud ecosystems. Terraform, a cloud-agnostic ISC tool capable of managing infrastructure across multiple cloud providers. 11.3 CI/CD with legacy systems, navigating the monolith and beyond. Not every company starts with greenfield microservices in the cloud. Many companies have existing large, often monolithic, applications that are critical to their business. Integrating CI/CD into these legacy systems requires different strategies and patience. Challenges: monolithic architecture. Large, tightly coupled codebases make small, frequent changes difficult. Changes in one part can impact many others. Manual processes. Legacy systems often have deeply entrenched manual build and deployment processes. Lack of test automation. Automated test suites are often sparse or non-existent, making continuous integration risky. Fragile environments. Production environments might be highly customized and difficult to replicate. Specialized technologies. Older languages, frameworks, or proprietary systems might lack modern CI/CD tool support. Cultural resistance. Teams might be resistant to change due to perceived risk or lack of new skills. Adaptations and strategies. Start small, iterate. Don't try to automate everything at once. Identify a small, low-risk part of the system or a single, frequently used deployment process to automate first. Celebrate small victories. Automate existing processes. Begin by simply capturing and automating the existing manual build and deployment steps. Even if imperfect, this eliminates human error and creates a baseline. Incremental modernization. Strangler fig pattern. Begin to peel off small, well-defined functionalities from the monolith and re-implement them as new, independently deployable microservices. The monolith continues to run, but its responsibilities shrink over time until it's strangled by new services. Each new service gets its own modern CI/CD pipeline. Improve test coverage incrementally. Invest in adding automated tests, starting with critical paths and new features. Even basic integration tests or characterization tests, tests that capture existing behavior without fully validating it, can build confidence. Containerize the monolith if possible. Even if you can't break down the monolith, packaging it into a container can help standardize its environment and make deployments more consistent and repeatable. Pipeline as documentation. The automated CI/CD pipeline itself becomes the documentation for how the legacy system is built and deployed. Dedicated old-school tools. Sometimes, you might need to use older build systems or deploy agents if the new ones don't fully support legacy quirks. The goal is automation, not necessarily using the latest and greatest tool in every single instance. Focus on culture. Recognize that cultural change is as important as technical change. Educate, train, and support teams through the transition. 11.4 The common thread. Principles over tools. Regardless of whether you're dealing with a cloud-native microservice architecture, a hybrid environment, or a monolithic legacy system, the core principles of CI/CD remain constant. Automation, reduce manual steps and human error. Version control, everything code, infrastructure, configuration goes into version control. Fast feedback, catch issues early. Repeatability, builds and deployments are consistent. Quality gates, enforce quality at every stage. Continuous improvement, always look for ways to enhance the pipeline and process. The specific tools and implementation details will differ, but by holding firm to these foundational principles, organizations can successfully adapt CI/CD to almost any technological context, driving efficiency, reducing risk, and accelerating the delivery of value across their entire software landscape. Chapter 12, The Road Ahead, Future Trends and Advanced Concepts in CI/CD. We've journeyed through the fundamentals of continuous integration and continuous delivery, exploring their principles, components, best practices, and adaptability to various contexts. But the world of software development is ever evolving. This final chapter looks towards the horizon, discussing emerging trends and advanced concepts that are shaping the future of CI/CD, pushing the boundaries of automated software delivery. 12.1 GitOps, the operating model for cloud native. GitOps is a relatively new paradigm that builds upon and extends the core principles of CI/CD, particularly in cloud-native environments and for managing Kubernetes clusters. Core idea: GitOps places Git, your version control system, at the center of your operational processes, making it the single source of truth for declarative infrastructure and applications. How it works. Declarative configuration. All infrastructure, Kubernetes manifests, cloud configurations, and application definitions are described declaratively, what should be, not how to get there. Version controlled. These declarative configurations are stored in Git. Automated reconciliation. An automated agent, often a Kubernetes operator like Argo CD or Flux CD, continuously observes the desired state in Git and the actual state of the infrastructure application. When a divergence is detected, the agent automatically takes action to reconcile the actual state with the desired state in Git. Benefits: enhanced security. All changes must go through a version-controlled, auditable process, pull requests. No direct manual changes to production environments. Faster disaster recovery. The entire system state can be recovered simply by applying the versioned configuration from Git. Consistency and reproducibility. Because Git is the single source of truth, all environments, dev, staging, prod, can be configured identically from the same Git repository. Simplified operations. Developers can manage infrastructure changes using familiar Git workflows. Relationship to CI/CD. CI is still used to build and test application code. CD, in a GitOps model, becomes primarily about pushing declarative configurations to Git, which then triggers the automated reconciliation process. 12.2 AI and machine learning in the pipeline. MLOps. As artificial intelligence, AI, and machine learning, ML models become integral to applications. The need for CI/CD practices specifically tailored for ML workflows has given rise to MLOps. Developing and deploying ML models introduces unique challenges not typically found in traditional software. Data management. ML models rely heavily on data. Managing data versions, ensuring data quality, and handling data pipelines become critical. Model versioning. Beyond code, the actual ML model, the trained artifact, needs to be versioned and managed. Experiment tracking. Data scientists run numerous experiments to find the best model. These experiments, along with their parameters and results, need to be tracked and reproducible. Model retraining. Models can degrade over time as real-world data changes, model drift. ML ops pipelines automate the continuous monitoring of models in production and trigger retraining processes when necessary. Complex pipelines. ML ops pipelines are often more complex, involving stages for data ingestion, data validation, feature engineering, model training, model evaluation, and model deployment. Impact on CI/CD. CI/CD principles are adapted to manage not just code, but also data, models, and comprehensive experiment metadata, often involving specialized tools for versioning data and orchestrating ML workflows. 12.3 Serverless first, the next evolution of deployment. Serverless computing, e.g., AWS Lambda, Azure Functions, Google Cloud Functions, abstracts away infrastructure management, allowing developers to focus purely on writing code, functions, that execute in response to events. This profoundly impacts CI/CD, reduced operational overhead. No servers to provision, patch, or scale changes the deploy and monitor stages significantly. Fine-grained deployments. Deployments become about updating individual functions rather than entire applications. Faster deployments. Small, isolated functions can be deployed extremely quickly. Pay-per-execution cost model changes the economics of deployments and testing in different environments. Impact on CI/CD. Pipelines become simpler from an infrastructure management perspective, but may require more specialized tooling for serverless application modeling, deployment, and monitoring. the focus shifts even more heavily to code quality and testing isolated functions. 12.4 Green software engineering and sustainable CI/CD. As software's environmental footprint becomes a growing concern, green software engineering aims to build, deploy, and run software in an environmentally friendly way. This extends to CI/CD, energy efficiency in pipelines, optimizing build times, leveraging efficient build agents, and powering CI/CD infrastructure with renewable energy can significantly reduce energy consumption. Resource optimization, efficient resource provisioning in the cloud, right-sizing instances, scaling down environments when not in use, directly translates to lower energy use. Green metrics, monitoring not just performance, but also the carbon footprint of your applications and CI/CD pipelines. Impact on CI/CD. Future CI/CD pipelines might integrate tools that analyze and report on the carbon emissions associated with builds and deployments, making sustainability a new quality gate. 12.5 Shift right testing and observability-driven development. While shifting left brings testing earlier, shifting right emphasizes testing and validating in production, a concept enabled by robust CD and observability. Testing in production. Using techniques like feature flags, canary releases, and A/B testing to expose new features to a small subset of real users in production, gathering real-world feedback and performance data. This is not about deploying untested code, but about validating tested code in the most realistic environment. Chaos engineering, deliberately injecting failures into production systems, e.g., Netflix's Chaos Monkey, to uncover weaknesses and build resilience, training teams to handle outages gracefully. Observability-driven development, using profound insights from production telemetry, metrics, logs, traces, to directly inform development decisions and prioritize improvements, continuously closing the feedback loop. Impact on CI/CD. Pipelines become more sophisticated in managing gradual rollouts, A/B testing, and integrating directly with production monitoring systems to make automated decisions about promotion or rollback. 12.6 The evolving role of the human in CI/CD. As CI/CD pipelines become increasingly automated, the role of engineers evolves. Human as orchestrator-designer. Engineers move from executing manual tasks to designing, building, and optimizing the automated pipelines themselves. Focus on business value. With more automation, teams can dedicate more time to understanding customer needs, innovating, and delivering features that truly add business value. Problem solver troubleshooter. When automation fails or unexpected issues arise, engineers apply their critical thinking and debugging skills to resolve complex problems. Continuous learner. The rapid pace of change in CI/CD and related technologies requires a commitment to continuous learning and skill development. Conclusion: the journey continues. Continuous integration and continuous delivery are not destinations, but ongoing journeys. They embody a philosophy of relentless improvement, automation, and feedback. While the specific tools and technologies will continue to evolve rapidly, the fundamental principles of driving business value through rapid, reliable, and secure software delivery will remain at the heart of CI/CD. By embracing these principles and staying attuned to emerging trends, you can ensure your software delivery pipeline remains a dynamic, efficient, and innovative engine, powering your organization through the exciting and ever-changing landscape of modern software development. The future promises even more streamlined, intelligent, and secure ways to build and deliver software. Your understanding of CI/CD provides the compass to navigate this exciting road ahead.